So I went ahead and I've been playing around with some other peripherals. I found a SPI based analog to digital converter. It's a pretty interesting device. Unlike the other ones I've worked with, this one actually does have SDI and SDO. And it also has a serial clock. And the other line it has is chip select. So as you can see here, we have our SDO, chip select, S clock, and here's our SDI. So the device that I have here is it is the MP3002, which I picked up off of or MCP3002. I also found this device in SparkFun. It has a couple channels, so you could measure a couple different analog inputs. So what you can see here is I have a couple CDS cells, and each one of these CDS cells is normally 10K, and they're basically a variable resistance that changes based off of light. And then I have a voltage divider going to the channel 0 and channel 1 pins with two other 10Ks, so it's theoretically it's dividing it in half when it has the highest light intensity going to the CDS cell. So at the light off, you can see that the voltage is 1.5. So let's go ahead and flip this light on quick, and it should change instantaneously. So you can see we've got 2.3 volts. Let's just start settling there. Okay, so what I thought we could do here for a quick demonstration is I'm going to show you reading out the values of the 10-bit value conversion, and we should be able to calculate that to 2.4 volts right now as it's standing. So let's give it a try. So we have a reset. I'm go ahead and we'll reset the communications. And then right here I'm selecting through channel 0 or channel 1. And this one right here is basically the command to start. I have the multimeter on channel 0. So let's go ahead and run channel 0 and see what happens. So based off of the output we have, let's see, we have 1. So that's going to be given the LSB, and right now it's giving me the MSB. So every 10 seconds it cycles through, because I only have 8 LEDs to work with, so I concatenated basically did a bit slice, and I'm showing the higher end, and then the very top bit is showing that the communications is done. So our binary should be 1 0. Let's go ahead and do that quick. So we're looking at 1 0 1 1 1 1 0, and let's wait another few seconds here until it comes up again. 1 1 1 1 0 1 1 0. Okay, so that's what we have here for binary. All right, so let's go ahead and convert that to decimal quick. So we're looking at 758. And right here, based off of this data sheet, see that we have this conversion here. So we're going to take this 768 that we have, we're going to divide it by 1024, and multiply it by the voltage that's supplying to the analog to digital converter, which is 3.3 volts. So we're going to take this 758, we're going to divide it by 1024, and we're going to multiply it by 3.3. And that should give us somewhere around 2.4. It gives us exactly 2.44, which is almost exactly what we're looking at here. So let's try to see what happens when the lights are off. Let's see if we get a different value. So now our conversion, let's go ahead and do that quick. We're looking at 0, 1, 1, 1, 0, 1, 1, 1, 1, 1. I'm sorry. Let's see. Let's look at this again here. 1. So it's gonna be 0, 1. 1, 1, 0, 1, 1, 1, 0, 0. All right, so that's what we should have here in binary. So let's go ahead and convert that to decimal. We're looking at 496. Let's go back to scientific, do a recall, divide it by 1024. And then multiply that by 3.3. We're looking at 1.53. Well, look at that. Exactly the same. So it works out really well. One thing about this device that you have to be careful about is the input impedance. And so for instance, in our case, we're looking at, I don't know, around like 5K or